Algorithmic game theory. Contents. Part 2. Computing in games. First, basic solution concept and computational issues. Second, the complexity of finding niche equilibria. Third, equilibrium computations for two-players games in strategic and extensive form. Fourth, learning regret minimization and equilibria. Fifth, combinatorial algorithm for market equilibria. Sixth, computational of market equilibria by convex programming. 7. Graphical games. 8. Cryptography and game theory. Second part, algorithmic mechanism design. 9. Introduction to mechanism design for computer scientists. 10. Mechanism design without money. 11. Combinatorial auctions. 12. Computationally efficient approximation mechanism. 13. Profit maximization in mechanism design. 14. Distributed algorithmic mechanism design. 15. Cost sharing. 16. Online mechanism. Part 3. Qualifying the inefficiency of equilibria. 70. Introduction to the inefficiency of equilibria. 18. Routine games. 19. Network formation games and the potential function method. 20. Selfish load balancing. 21. The price of anarchy and design and the design of scalable resources allocation mechanism. 22. Part 4. Additional topics. 22. Incentives and pricing in communication networks. 23. Incentives and peer-to-peer systems. 24. Cascading behavior in networks, algorithmic and economic issues. 25. Incentives and information security. 26. Computational aspects of prediction markets. 27. Manipulation-resistant reputation systems. 28. Sponsored search auctions. 29. Combinatorial evolutionary games theory. Forward. As the Second World War was coming to the end, John von Neumann, arguably the foremost mathematics of the time, was busy initiating two intellectual currents that will shape the rest of the 20th century: game theory and algorithms. In 1944, 16 years after the min-max theorem, he published with Oscar Morgenstern his Games and Economic Behavior, thus founding not only game theory but also utility theory and microeconomics. 2 years later, he wrote his draft report on the EDVAC, inaugurating the era of the digital computer and its software and its algorithms. Von Neumann wrote in 1952 the first paper in which a polynomial algorithm was hailed as a meaningful advance, and he was the recipient shortly before his early deals 4 years later of a Gödel's letter in which the P versus NP questions was first discussed. Called von Neumann have anticipated that his twin creations would converge half of the century later. He was certainly far ahead of his contemporaries in his conception of computation as something dynamic, ubiquitous, and enmeshed in society, almost organic. Witness his self-reproducing automata, his fault-tolerant network design, and his prediction that computing technology will advance in lockstep with the economy, for which he had already postulated exponential growth in his 1937 Vienna colloquium paper. But I doubt that von Neumann could have dreamed anything close to the Internet. The ubiquitous and quintessentially organic computational artifact that emerged after the end of the Cold War, a war, incidentally, of which von Neumann was an early soldier and a possible casualty, and that was fortunately fought mostly with game theory and decided by technological superiority, essentially by algorithms, instead of the thermonuclear devices that were von Neumann parting gift to humanity. The Internet turned to the tables of students of both market and computation. It transformed, informed, and accelerated markets while creating new and therefore unimaginable kind of markets in addition of being itself in an important way a market. Algorithms became the natural environment and default platform of strategic decision making. On the other hand, the Internet was the first computational artifact that was not created by a single entity, engineer, design team, or company, but emerged from the strategic interaction of many. Computer scientists were for the first time faced with an object that they had to fill with the same be well aware with which economics have always approached the market. And quite predictably, they turned to game theory for inspiration. In the words of Scott Schenker, a pioneer of this way of thinking, who has contributed to this volume, the Internet is an equilibrium. We just have to identify the game. A fascinating fusion of ideas from both fields, game theory and algorithms, come into being and was used productively in the effort of to eliminate the mysteries of the Internet. It was come to the called algorithmic game theory. The chapters of this book, a snapshot of algorithmic games theory, at the approximate age of 10, written by a galaxy of leading researchers, succeeded brilliantly, I think, in capturing the field's existence, breadth, accomplishment, and promise. The first few chapters recount the ways in which the new field has come to grip with perhaps the most fundamental cultural incongruity between algorithms and game theory. The latter predicts the agent equilibrium behavior, typically with no regard to the ways in which such a state will be reached, a consideration that would be a computer scientist's famous concept. Hence, algorithms for computing equilibria, Nash and correlated equilibria in games, price equilibria for markets, have been one of algorithmic games theory's earliest research goals. This body of work has become a valuable contribution to the debate in economics about the validity of behavior prediction. Efficient computability has emerged as a very desirable feature of such predictions, while computational interactability sheds a shadow of impossibility of a proposed equilibrium concept. Computational models that reflect the realities of the market and the Internet better than the von Neumann machine are, of course, at a premium. There are chapters in these books of learning algorithms as well as distributed algorithmic mechanics design. The algorithmic nature of mechanism design is even more immediate. This elegant and well-developed sub-area of game theory deals with the design of games with players who have unknown and private utility, such that the equilibrium of the design games, the designer's goals, are attained independently of the agent utility. Auctions are an important example here. This is obviously a computational problem, and in fact, some of the classic results in this area had been subtly algorithmic, albeit with little regard to complexity considerations. Explicit algorithmic work of mechanism design has in recent years transformed the field, especially in the case of auctions and cost sharing. For example, how to recover the cost of the internet service from consumers who value the service by almost known to only to them, and has become the arena of especially intense and productive cost fertilization between game theory and algorithms. Those problems and accomplished are recounted in the book's second part. The third part of the book is dedicated to the line of investigations that has become called the price of anarchy. Selfish rational agent reach an equilibrium. The quasi-theory arises exactly how inefficient is this equilibrium in comparison to the idealized situation in which the agent will strive to collaborate selflessly with the common goal of minimizing total cost. The ratio of those quantities, the cost of an equilibrium over the optimum cost, has been estimated sufficiently in various internet-related setups, and it's often found that anarchy is not nearly as expensive as one might have feared. For example, in one celebrated case related to routing with linear delays and explained in the routing games chapter, the overhead of anarchy is as most 33% of optimum solution. In the context of internet, such a ratio is rather insignificant and quickly absorbed by its rapid growth. Viewed in the context of the historical development of research in algorithms, this line of investigation could be called the thought compromise. The realization that optimization problems are interactable lead us to approximation algorithms. The inability of information about the future or to lack of coordination between distributed decision makers brought us online algorithms. The price of anarchy is a result of our future obstacle. How the distributed decision makers have different objective functions. Incidentally, it is rather surprising that economics has not studied this subject of strategic behavior because the advent of the internet. One explanation may be that for economists, the ideal optimum has never an available option. In contrast, computer scientists are still looking back with nostalgia to the good old days when artifacts and processes could be optimized exactly. Finally, the chapters of additional topics that concludes the book, peer-to-peer systems and informational markets, apply demonstrate the young area impressive breadth, reach, diversity, and scope. Books, a glorious human tradition apparently inspired by advance of the internet, have a way of making and focusing a field of accelerating its development. 7 years after the publishing of the game theory of games, Nash was providing his theorem on the existence of equilibria. Only time will tell how this volume will sway the path of the algorithmic game theory. Paris, February 2007. Christos A. Papadimitrios.